Hey everybody. All right, so this is your instructional video on ocean water properties. So this is a new unit. Start on a new page, in your interactive notebook. I have linked some videos on the weekly planner for this activity. So also make sure you watch those videos. Two of them I'm going to show you within this instructional video because they're rather short and I feel like I need to show them to you so I can explain them. Okay. All right. So salinity. We've talked a lot about salinity, especially in the last unit when we talked about desalinating salt water. So salinity is just simply the amount of salt in seawater. Okay, the average amount of salt in the seawater is 3.5%. Okay. Usually, though, there are things that can increase that amount or decrease that amount. So we're going to talk some about that in this video. Okay. And I wanted to show you my shirt because I wore it because I knew I was recording this video today. And it reads, as you can see, don't be so NaCl. And if you remember, NaCl is sodium chloride, which is salt. So don't be so salty. Get it? Okay. All right. Just a little humor there. Now, okay. So take a look at this animated picture of a glass of salt water. Now, as you learned in the last unit, water, H2O, is the universal solvent. And that is simply because, as you probably remember, water can dissolve most substances like salt. So when you pour some salt crystals into a glass and then you add water, the water is going to go to work and dissolve that salt. And this is what it does. It actually pulls apart the atoms of sodium chloride, okay? The sodium carries a positive charge and the chloride carries a negative charge, okay? So when the positive and negative ends of H2O, of the water molecule attached to the opposite, it pulls it away from the actual other piece. So let me explain it another way. Let's say the positive end of the hydrogen atom in H2O connects to the negative end of this sodium chloride, which would be the chloride. That hydrogen is going to pull on that chloride atom and get it away from the sodium atom. Okay. So it's sort of like a tug of war. All right. That's called dissociation of salt. Okay. So I'm going to click on this video and I want you to watch it carefully. It's just a 1-minute video. It'll explain how that is done. Okay. So watch.
Sodium chloride crystals are held together by attractive forces between the positively charged sodium and negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround.
Okay, see, I'm going to pause it because I want you to notice the negative ends of the hydrogen are going to attract to the positive end. All right. And I'm sorry, back up, Miss Lael. The positive ends of the hydrogen, I apologize, are attracting to the negative ends of the chloride. And likewise, the opposite, the negative end of the oxygen is going to attract to the positive end of the sodium. Okay. Opposites attract. Think of it that way.
The positively charged sodium ions. The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions. Gradually, the entire crystal dissociates into solution.
Okay, and that is dissociation, meaning dissolving. Okay, all right. So things that can alter that average 3.5% salinity level. Heavy rains, precipitation. Now remember, guys, we're only talking seawater. Lakes and rivers are fresh water, all right? So I'm not talking about lakes and rivers and streams. I'm talking about the oceans. Now, in the ocean, if there is a large amount of rainfall, then it can sort of, I guess you could say, water down that salinity level. So the amount of salt, it will seem to decrease, okay? That level will decrease below that average 3.5%, okay? You remember how the mouth of a river is where it is dumping into the ocean? Well, that means that that part of the ocean is going to have a lower salinity level than the average 3.5% because you have all that fresh water from the river dumping into the mouth, at its mouth. That's where it dumps out into the ocean. So that water around that area of the ocean, that salinity level will be decreased. And we call that water brackish because it's a mixture of fresh and salt water, the fresh water coming from the river and the salt water, of course, in the ocean. We call that water brackish water. And anytime there is a period of very dry weather, like a drought, droughts can exist over the water just as much as they can exist over land, okay? So that just means a dry period of time where there's no precipitation and there's a high amount of evaporation. So the water, the H2O in the seawater is evaporating, but the salt is being left behind. That will also increase the salinity level, okay? One other one that I didn't feature in here, though, and it's kind of hit or miss, so I didn't feature it as a thing that can change the salinity, but think about it where icebergs are, because just like water, the H2O can only evaporate, it is also the only thing that can freeze. So when you see an iceberg in the middle of an ocean, it is pure solid water. It's fresh water in solid form, okay? So that means that the seawater below that iceberg and surrounding it might be a little bit saltier because the salt can't freeze. Just like the salt can't evaporate when heat is added to water, the salt can't freeze when the water temperature drops, okay, below that freezing level. Okay, so something to think about. But sometimes that's a bit inconsistent because we have the icebergs are, they are melting now. So that actually is watering it down. All right, so I want you to take a look at this map just for a moment. And these are the surface waters. It's only the measurement of the surface water, and it's measuring the salinity level. Once we get deeper into the ocean, past what we call the surface zone, and we start to get into the transition zone of our seawater, the ocean, the salinity level is pretty constant. It's pretty much the same, okay? And we'll talk about those zones of our of our water column in our next unit. We've got the surface, the transition, and then the deep. And once we get to that transition zone, it's pretty constant, the salinity level. So we're just talking in this map about just the salinity level on the surface of the water in the oceans, okay? So when you take a look at the purples and the blues, those darker colors, okay, the salinity is a little below normal, okay? Now, when you take a look at it's right around, 35 PSU, that would be 3.5, okay? The PSU is just talking about the salinity units, okay? It's the salinity units. So you want it right about 35. So anything that you see in the green is good. That's about average. When you get into the yellows and the oranges, they're very, very dark. That is closer to the equator, and the drier landlocked areas right around here, okay, in between Europe and Africa. And the salinity levels are quite high, higher than normal. And that's because of the dry weather and the rate of evaporation, okay? But when we look at the purples and the blues, the salinity level is a little low, and that's what I was talking about just a minute ago, well, you would think around the icebergs that the salinity level will be a little high because the ice can't melt or it can't freeze. But because of the global warming and because of the icebergs that are beginning to melt at a faster rate than normal, than average, it is lowering the salinity level in the seawater. Okay. It's caused because it's when the ice melts, that's fresh water. So it's melting into that salinity, into that seawater, and it is lowering the average salinity level. Okay. All right. So we're going to take a look at this. This is a tracker that shows the changes, and you see the timer right here in the upper corner, in the upper right corner. And this is over a 5-year period. Okay. So right now we're in November of 2015, December. Now we're into 2016. Okay. And here's Africa. And you can see it looks a lot like what we were just looking at. You can see how dry the weather is. Now, hold on. Let me stop right here. Okay, I'm going to pause. Look at the date. This is October, early October of 2016. Now, here's the United States right here. And if you take a look, the salinity levels, that orange, remember, indicates that it's higher than normal. And that's because we're coming out of a dry period. We had a bit of a drought in 2016. It wasn't too bad, not like the ones that I showed you in 2008 or 2007 to 2008, all of that. This, this wasn't quite as bad, but it was still quite dry. But if you take a look over here on the Pacific side of the coast of the United States, it's in the blue. So it's a little bit actually above normal. Below normal for the salinity level. We got high salinity levels over here and a little bit lower than normal. And a lot of that has to do, again, with the melting of the polar ice caps and it dumping that fresh water and the currents, the ocean currents dragging that fresh water down to closer to the equator, below the poles. So as it rotates, keeps rotating, over the 5-year period, you're not going to see a huge difference, okay, in the changing salinity levels. It's pretty constant. If you take a look again here, 2018, okay, I'm going to try to stop it right about, okay, this is right about the same time, just 2 years later. Okay, instead of early October 2016, now we're at late September of 2018, 2 years later. We've got a little bit more of a standard of an average here in our salinity levels. Okay, so it does change with the weather because of droughts, because of precipitation. That can definitely change it. Okay, all right. Now, the higher the salinity level, the higher the density in the ocean water. Now, in the last unit, remember, we also learned that the colder the water, the more dissolved oxygen it has, and it will sink, just like cold air. Remember when we were talking about if you have a 2-story home, a lot of you said it's warmer upstairs than it is downstairs. And that has to do with the cold or the oxygen, the gas that is in cold air. It has more dissolved gas. The same thing with water. It's got more dissolved oxygen gas in colder water, so it's going to sink. But when we have a lot of salt in the water, if it's higher than average, the higher than that 3.5%, then that is going to sink a bit because it's going to have a higher density. The higher the salinity, the higher the density. Okay, so some of our other properties, the gases that are dissolved in ocean water are mainly dissolved oxygen and, of course, dissolved carbon dioxide that the plants are taking in the waters. Okay, all right, and like we said, go ahead and write that down again. Cold water can hold more dissolved oxygen than warm water. Same thing with air. Okay. All right, so pause this if if you are still writing. I'm going to go on to this map. Now, this map is showing something different. We're not talking about the salinity levels in this map. We're talking about the oxygen levels of the surface water, okay? So this time, if you take a look, the darker colors, okay, it sort of goes a little the opposite. The darker colors mean it's holding less dissolved oxygen, and that's not necessarily good, okay? The blues and the purples. The darker colors like the yellows and the orange and the dark red means that the water holds more dissolved oxygen. So it makes sense that around the equator, which is all right here down the middle, we're going to have the blues and the purples because that's warmer water. So that's holding less dissolved oxygen than up here at the poles, which is the darker red. Okay. Now, remember, we studied and discussed dissolved oxygen levels in our water because we use that as an indicator for good or bad water quality. The higher the oxygen levels, the colder the water. So the healthier it is for the fish, okay? The warmer waters, if it's too warm, that could indicate an unhealthy water, okay? But when you're talking about around the equator, the fish that are around the equator are adapted to live in those warmer waters, okay? So like marlin and really large fish that you can catch off the coast of like, the Florida Keys and stuff. People go fishing down there and they always want to catch a marlin because it's a huge fish. They thrive in those warmer waters. They would not survive here in the colder climes where the water is so cold, okay? All right. Now, this just is a graph that shows you the water temperature compared to the oxygen solubility, the dissolved oxygen. And the dissolved oxygen is measured in milligrams per liter, while the water temperature is measured in Celsius, not in Fahrenheit. Okay, so 0 degrees Celsius is freezing. Okay, that's the temperature that water begins to freeze. So it makes sense that we've got 14 or 15, between 14 and 15 milligrams of oxygen, dissolved oxygen at 0 degrees versus we don't have any oxygen when the water is at 100. All the oxygen is taken up, okay? All right. This is just a little joke. The little boy says to the teacher, I thought you said that the chemical composition for water was H2O. Get it? HIJKLMNO, H2O. Okay. Buoys. You've probably seen these. If any of you ever go boating in a lake, you probably see buoys. Now, buoys we use, oceanographers will use them to monitor ocean temperature and salinity levels. Okay, now if we're talking about lake water, though, we're only using the buoys for for water temperature because salinity isn't found in lake waters. Okay. If it is, that's not good. If we've got salinity in our lake waters, that's not a good thing. All right. So we use those buoys because we always want to monitor temperature and salinity levels. And we need to gather that data. It's pretty much hourly, 24/7, and compare it from year to year or month to month, week to week, all of that year to year. And to see if it's increasing, decreasing, or inconsistent, because if it is, then we need to figure out what's causing those inconsistencies from year to year. Okay, the other thing about ocean water is it isn't just the temperature that changes when you get deep. Also, the amount of light and the pressure also change. So when we're on the surface of the ocean, we're on the surface. So the sun's out and the light, it's very bright. So we can kind of see through the beginning parts of the ocean. Okay. There's a lot of light in the surface zone of the ocean. The temperature is probably warmer. The pressure is low. Okay. All of that. And then we go deeper. And the next zone, as I mentioned earlier, is called the transition zone. That's where the light changes. We have a lot less light in the transition zone. The temperature is starting to get a little colder, and the pressure is starting to increase. And pressure is just the definition of pressure is the amount of weight pushing downward on something, okay, like on you. So when you go deeper into the pool, you might feel a little bit of pressure in your ears, okay? That's because all the weight of the water above your head when you're in the deep end of the pool is pushing downward on you. And when you're at the surface of the pool, you don't have that much pressure pushing you downward, okay? Or pushing down on you. Now, after the transition zone, we'll go back to the zones. After the transition zone, then we're in the deep zone. And the deep zone is where it's really, really super cold. There is no light at all, and the pressure is super heavy. So much so that we can't explore the deep zones of our oceans unless we are inside a submersible, okay? Because the weight of that water would literally crush your bones if you were swimming. Now, you might say, well, look at this dude. What's he doing then? Well, he's not in the deep zone. You can see a lot of light above him. So he is still kind of in the middle between the surface and heading to the transition zone. All right. So that's okay. But you got to be in a submersible like this. Okay. You may have seen videos from or movies where they have submersibles. If you've ever watched any of the films that take place underwater, you might see those submersibles. But you got to be in a submersible. You would never survive outside of it because of the pressure and the cold. All right. And it's super, super dark. Okay. If you remember Finding Nemo, when they found the anglerfish with the little light, okay, that's an actual real fish. And they got it pretty right with the size and the shape and the teeth and all that of the anglerfish. But he bioluminesces. And bioluminesce means that he, like this dude, it looks kind of like an alien, but that's actually a plankton, are able to create their own light within their bodies. The body chemistry that they have, they're able to create their own light because they survive in the darkest parts of the ocean, okay? All right, and the reason they bioluminesce sometimes is to ward off predators, but sometimes it's also, like the anglerfish in Finding Nemo, attracts the predators, okay? All right, these are the 3 videos that I am going to link on your weekly planner, and make sure you watch them, okay? All right, here are your statements. On average, ocean water is about 7% salt. No, that's twice as much as it's averaged. 3.5% is the average, okay? Precipitation can lower the salinity of ocean water. Agree. Yes, it can. Because when precipitation falls, that's fresh water and it's watering down the seawater. So the salinity level drops. Fish in the ocean breathe oxygen. Correct. Okay, that's why we need a lot of dissolved oxygen in the water. As you go deeper in the ocean, the water temperature decreases. That is also correct, because as you lose and move away from that light, then obviously the temperature is going to decrease as well. As you go deeper in the ocean, the pressure decreases. That is incorrect. The pressure will increase, not decrease, because as you go deeper, you have more water above your head, and the weight of that water is pressing downward, okay, on top of you. All right, so I hope that helps, and please make sure that you take a picture of your notes, you submit it for your assignment, and email me if you have any questions at all. Okay? Take care.